Look at the structures around us. Massive hydroelectric dams, sprawling highways, the dense grids of the post-war welfare state. They are all anchored by a single, inescapable material. We rely on it for our physical survival, to keep the water out and the bridges up. Yet we walk over it every day without a second thought, at least until it cracks. Understanding the modern world requires viewing cement as an actively evolving technology, one that iterates constantly to keep the machinery of society functioning. In 1860s, Sweden was trying to industrialize, but they hit a severe physical bottleneck. To build ports and railways, the nation needed cement, and every single pound of it had to be imported at an incredible cost. In 1870, an engineer named Otto Bernard Fonahelm decided to look locally. He ran chemical analyses on the clay and limestone in western Skåne, testing to see if Swedish soil could match the strict standards of the world's best English Portland cement. His tests proved it could. That chemical success led directly to the founding of Skånska Cement AB in 1871. Within a few years, industrial-scale domestic production was a physical reality in towns like Lomma. Clearing this material hurdle was mandatory. A nation cannot scale its infrastructure if it relies on other countries to ship its own foundation. With unlimited domestic material unlocked, the factories in Lomma and Limhamn scaled up rapidly. But this rapid expansion inadvertently concentrated a massive labor force in one place. The long hours and intense conditions sparked violent labor chaos. Strikes crippled production, climaxing in the summer of 1908, when radicalized workers attacked a ship housing imported strikebreakers in Malmö Harbor, detonating a bomb that killed one man and injured dozens more. The factory owners realized their operations could not survive this level of disruption. They needed a systemic solution to manage their workers, leading them to form the Swedish Building Materials Federation, or BEF, in 1908. This organization allowed the employers to negotiate the first national collective agreement in 1909. It imposed strict, standardized rules on hours and wages to stabilize the workforce across the entire industry. The resulting industrial peace was not an accident. The industry designed a rigid social framework with the same precision they used to calculate the load-bearing capacity of their concrete. Fast forward to post-war Sweden. The labor force is stable, but the nation is desperate for rapid urban housing. Traditional ring kilns and manual pouring methods are far too slow to meet the demand. Production speed becomes the new bottleneck. To fix this, the industry implemented massive 145-meter electric rotary kilns. By combining these with a wet method, where water was added before milling, plants could run day and night, pushing out an exponential volume of material. At the same time, construction sites evolved. Instead of pouring concrete slowly into wooden molds on site, builders shifted to reinforced, pre-fabricated elements that arrived ready for rapid, modular assembly. This combination of high-volume cement and prefab elements supplied the Million Program, a sweeping government initiative that built 1 million new homes in just 10 years. By bypassing the speed bottleneck, the industry provided the material needed to move millions of people into new urban centers in a single decade. As the scale of production increased, a hidden chemical consequence began to accumulate. In a process called calcination, limestone is heated to extreme temperatures. Carbon dioxide is stripped away and released into the atmosphere. This single reaction generates a carbon footprint that dwarfs other global emissions, making it the industry's most critical bottleneck. The foundation of modern society is currently hurting its own future. To survive, the material must be re-engineered from scratch. The industry's response to this bottleneck is Zero Vision 2030, an initiative racing to engineer carbon-neutral concrete within a single decade. Plants are swapping fossil fuels for biomass, but the true fix requires capturing carbon emissions directly at the exhaust stack before they ever hit the atmosphere, and finding ways to permanently lock them away. Throughout its long history, cement has functioned as a responsive technology, constantly iterating whenever a new societal bottleneck appeared. Our ability to navigate the climate crisis will depend heavily on whether we can successfully engineer this final iteration of our oldest building block.